Welcome to this instructional video for chapter 17. So we've been talking about beta oxidation. We have to be able to take fatty acids that are liberated from triglycerides, triacylglycerols, and break them down. And what we had to do was activate the fatty acids to fatty acyl-CoA. That fatty acyl-CoA was transported into the mitochondrion, and that's where beta oxidation occurs. Now we need some type of chemical strategy to systematically break down a fatty acyl-CoA molecule and remove 2 carbon units at a time, and those 2 carbon units will be liberated as acetyl-CoA. And this is where we left off last time. And don't get lost on the analogies here. Don't let the analogies go by you, because we've seen a lot of this type of chemistry before. So here we are. Here, let's just say we take palmitoyl-CoA from palmitic acid. It's got 16 carbons. How are we going to break this down to 8 acetyl-CoA? That's what beta oxidation will do for us. Okay. Well, the first step in this was, the overall strategy was to realize that this is a beta bond, and it is labile. It can be easily broken, but the issue is, for this bond to be easily broken, the beta carbon, which we have labeled right there, has to be reactive. And as it stands, that's not a very electrophilic carbon. So we have to do 4 steps to get that carbon more electrophilic so it can be attacked by the coenzyme A nucleophile to allow a new CoA molecule to be made and liberate acetyl-CoA. So the first step was acyl-CoA dehydrogenase. Again, converting this saturated system to a double bond, an unsaturated system. That's a redox. That's 2-electron oxidation coupled to a 2-electron reduction of FAD that goes to FADH2. One of our reduced cofactors we can use in the electron transport system. This created a trans delta 2 enoyl-CoA derivative. I kind of made a big deal about, hey, we talk about trans fats are bad, but we make trans fat derivatives in the breakdown of saturated fatty acids. We make trans intermediates. So the double bond, as you know from organic, you can hydrate a double bond, but this needs to be done in a stereospecific manner, so we need an enzyme. If you need to do a hydration reaction, you need a hydratase enzyme. So enoyl-CoA hydratase stereospecifically adds a molecule of water across the carbon-carbon double bond to make our secondary alcohol that we see here shown. And this was very important because now we've just made, through what I call redox construction, this hydratase enzyme catalyzes a redox construction reaction. It's not redox, it's redox construction. It makes a molecule more easily oxidized, and we know that because we have our beacon of oxidation, our secondary alcohol type arrangement in this derivative here. So let's keep going, okay? And again, don't overlook the analogies. Succinate dehydrogenase from the citric acid cycle in the first reaction, fumarase from the citric acid cycle in the second reaction. So let's take the molecule that's at the bottom of this page. It's been moved to the top of the next page. And we've got to keep going here, right? So we take our oxidative landmark and we're going to convert that to a carbonyl. We did that all day long in Biochem 1. And of course, no big surprise, the enzyme that does this, dehydrogenase, and now we make a molecule of NADH. So this 2-electron oxidation is coupled to a 2-electron reduction to make NADH. Now we have a beta carbon. This is our buddy beta right there. That's much more reactive. It's a carbonyl. We know carbonyl carbons are electrophilic. ready to be attacked by a nucleophile. And we also know that the rest of this molecule is a good leaving group through the principles of beta reactivity. So the last step is catalyzed by an enzyme called thiolase, and this is thiolysis. And of course, you should know what thiolysis means. It means to break with sulfur, right? To break with a with a molecule that has probably a thiol group, SH. So really what's going on here in this last step is the following. Let me give you a little bit of a abbreviated rundown on this. So coenzyme A has a thiol group, but probably in the active side of this enzyme, this becomes deprotonated, and a much more powerful nucleophile thiolate ion. And then, oh, here we go. Look at this. We just spent all of this energy. Well, we didn't spend all this energy. We spent all this metabolic time, if you want to say, or metabolic process to make this right here. That's what we just made. And this is our beta carbon. Right there. And so now the beta carbon is much more reactive than it used to be. The beta carbon used to be a CH2, unreactive in this sense. The carbonyl is much more reactive. So here we go. We can have a nucleophilic attack. I'm not going to show you the entire mechanism of this. I think you get the point. And then ultimately what's going to happen is this is going to break. This bond's going to break. This is called beta reactivity, right? Beta reactivity. And it's going to leave a good leaving group, which ultimately will make acetyl-CoA. And that's what we get. We now, after thiolysis, and thiolysis is we're breaking this bond. We're breaking this bond right here with a sulfur. That's why it's called thiolysis. But we needed the beta carbon to be more reactive than it was at the beginning of this process, and it is. So what do we have? We have a C14 fatty acyl-CoA, and we have a 2-carbon derivative acetyl-CoA that can go into the citric acid cycle, and that's what we wanted. All right. Well, Mr. C14 fatty acyl-CoA, let's start over. Let's do the same 4 reactions again. And then you'll get a 12-carbon fatty acyl-CoA. Hey, do it again. Until you do a total of 7 times, you're going to get 8 acetyl-CoA. All right. Don't lose the big picture here, because there's some analogies as well. The analogy for this enzyme is malate dehydrogenase from the citric acid cycle. So if we go to the next page, this kind of gives us the big picture. You know, in Biochem 1 we talked about catabolism and anabolism was metabolism. You can break it up into those two things. Catabolism largely involved the oxidation of intermediates, and we saw that in glycolysis a little bit, the citric acid cycle for sure, and we just saw this in beta oxidation as well. Well, look at these common oxidation strategies. Wow. We just did this. This is what we just went over. And we liberated 2 reduced cofactors for every 1 fatty acyl-CoA we started with. Well, again, please look at this closely. In the citric acid cycle, at some point, we also did something very similar, right? Look at this. We had a saturated CH2CH2 that gave us a double bond. We hydrated to give an oxidative landmark, and then we did another redox reaction. We saw this in the citric acid cycle. Now, if you look closer, or look into the breakdown of amino acids, the catabolism of amino acids, you see a very similar oxidative strategy. We are not going into this in great detail, but I do want you to kind of get the big picture here. Here's a derivative. Here's a CoA derivative of the amino acid isoleucine. Okay, and so what you see is to break down isoleucine. And again, we've started at an intermediate here, a CoA derivative of it. But to break it down further, it uses the exact same oxidation strategy. So, ladies and gentlemen, if you want to break down fats, you have this oxidation strategy. In the citric acid cycle, where you break down glucose, and you also break down fats, you have this common oxidation strategy. And then you also have this similar oxidation strategy in place for some amino acids, the catabolism of some amino acids. Now, what I do want to do is take a bit of an aside, and let's call this intermediate A. Because at some point, if you take isoleucine, and again, think about, do proteins have caloric value? You should think about that. And is the caloric value of proteins more similar to fats or more similar to carbohydrates? We do have to break down, at times we do break down amino acids for energy, for caloric purposes. And this is just part of one of the pathways this can be done. What I want to do a little bit more before we move on is, what if we had something like isoleucine? How would we go from isoleucine to this intermediate A? How would we get there? Because it's going to demonstrate some other common metabolic features, and it's also going to feature an enzyme that I want to discuss in this class. So let's do this. I'm going to insert a new page, and let's start with the amino acid isoleucine. There we go. And you know what? Let's do this. The side chain isn't in play on this. Let's just make this R. But I do want you to think about this being isoleucine, and I think the notes on the previous page said something similar can happen to isoleucine. What did it say here? Leucine and valine. So let's just do this generally. Let's just make the side chain an R group because the side chain is not coming into play. Ladies and gentlemen, there's a very important enzyme on your enzyme sheet you got in Biochem 1. We didn't talk a great deal about it in Biochem 1, but you need to know about this enzyme, and now it's the time for me to re-emphasize it. It's called a transaminase. And I'm leaving out some of the details, but I want you to get the big picture here. A transaminase can convert an alpha amino acid such as isoleucine, valine, or leucine, to an alpha keto acid, So let me draw the structure of this. There we go. This is an alpha keto acid. This is done by a transaminase. Now there's another molecule involved in this reaction, but I just want to focus just on this part of the transaminase activity. I think you should know this because a transaminase, especially for the MCAT, transaminases convert alpha amino groups to alpha keto groups. So by a complicated mechanism we're not going to go over, this amino group is gone and we have in its place a carbonyl. Again, not easy chemistry to do, but transaminases can do this fairly well. So, again, what are we doing right now? I'm taking a little bit of an aside to briefly mention the catabolism of amino acids, something we don't talk a lot about in this class, but I do want to highlight a few things because we just talked about amino acid breakdown uses at some point a similar oxidation strategy as we saw in beta oxidation and the citric acid cycle. So I'm trying to get to this intermediate on page 13, sorry, on page 13. How would you get to this intermediate that I'm just labeling A so we could undergo oxidation of the side chain? Okay, so I'm trying to show you how we could get to intermediate A. But the side chain's not involved in this, so I'm just labeling it R. Okay, well this next bit is going to be like a walk down memory lane because now we have to convert this to a CoA derivative, our intermediate A, if you will. And so this is intermediate A on page 13. And again, I'm not specifying the side chain. So, wow. At this point, if you can kind of muster up some recollection of Biochem 1, there's a lot of questions to be asked here. What type of reaction am I showing you going from this alpha keto acid to this intermediate A? Well, not to spend 3 hours on this, let me just kind of throw it at you. With this enzyme, and first of all, this enzyme is called branched chain alpha keto acid dehydrogenase. And so obviously what I'm showing you, R, is going to be a branched chain side chain. So this reaction I'm showing you now is prominently for these branched chain side chain, amino acid side chains that have, are hydrocarbons and have a branch. So this enzyme, ladies and gentlemen, catalyzes an oxidative decarboxylation. Now I didn't even show you that, but CO2 has to come out of here, right? So what did we say about oxidative decarboxylations in Biochem 1? Well, probably one of the best examples of that was pyruvate dehydrogenase. Okay, pyruvate dehydrogenase that catalyzes the bridge reaction. This is very similar. Okay, so you're going to have an NAD plus come in to make NADH. Carbon dioxide comes out. So this is an oxidative decarboxylation. Okay, and we'll talk about why it's an oxidation in a minute, just to review that. What else do you need? Well, you need CoA to come in because we've added coenzyme A on here. What else do we need to run this reaction? Ladies and gentlemen, isn't it true that we did alpha cleavage? Isn't this alpha cleavage we decarboxylated? Yes. We need our old friend, I hope you haven't forgot about, TPP. Again, this is an oxidative decarboxylation. Let's review why that's even true. If you look at the carbons that underwent change in this reaction, this is +3, this is +4, this one up here is +2, this is +3, and so it looks like we went from a net oxidation number of the carbons undergoing chain of +5 to +7, ladies and gentlemen, going from an alpha keto acid to this CoA derivative I'm labeling as A. It's a 2-electron oxidation coupled to a 2-electron reduction of NAD plus to NADH. Oxidative decarboxylation requiring TPP. So again, there's an analogy here, and the analogy is pyruvate dehydrogenase of the bridge reaction that we saw between glycolysis and citric acid cycle. Again, I'm trying to point out to you common metabolic schemes used in catabolism. Something else that I want to add to this. Branch chain alpha keto acid dehydrogenase is an enzyme that can be mutated. It has a variety of mutations. One or more of these mutations can lead to an enzyme, one or more mutations of this enzyme can lead to a very serious genetic disease in children, because if they get this disease, it typically leads to it leads to an impaired mental status. They fail to thrive and typically will not progress very far into adulthood. This disease, and I bring this up because then you're going to see why I bring it up. You will, if you go to medical school, possibly graduate school, you will hear about this disease. It's called maple syrup urine disease, and it is some impairment through mutation of branch chain alpha keto acid dehydrogenase. If there's a mutation in this enzyme, if this enzyme is not as active or not present, then you build up, or if you're a child and you have this issue, you are not able to metabolize branch chain amino acids, and branch chain amino acids have this type of sweet maple syrup smell that can be detected in urine, and not being able to process branch chain amino acids is a serious problem that can lead to many problems, I guess, with one of them being neurological issues. Anyway, likely you will see this disease again in the future, especially if you go into medicine. All right, so let's keep going. Let's sum all this up. So we're starting here with palmitoyl-CoA, a 16-carbon fatty acid, and how much ATP can you make per one palmitoyl-CoA molecule? This is just like in Biochem 1. How many molecules of ATP can you make per breakdown of glucose? Well, now we're talking about palmitoyl-CoA. And we have to think about making ATP directly, which I don't think we did. Did we make any ATP directly in beta oxidation? Don't recall that at all. Okay? But we did make a lot of reduced cofactors. And you know from Biochem 1 that when you make reduced cofactors, they go to the electron transport system, and then here is our kind of conversion factors for that. Okay. Well, the first two reduced cofactors we make in basically directly from beta oxidation. This was step 3. Stage 1. Remember, stage 1 was those 4 reactions that occurred to break off 2 carbons of a fatty acid to make acetyl-CoA. And so step 1 is activation of a fatty acid. Step 2 is transport. Step 3 is the breakdown. And then stage 1 is really those 4 reactions that we just went over. We make, for every palmitoyl-CoA molecule you start with, remember, the process, those 4 reactions, that sequence of events has to happen 4 times. Excuse me, not 4, 7 times. 7 times to get 8 acetyl-CoA. So that's why the numbers are 7 here and 7 here. 7 FADH2 times 1.5 ATP equals 10.5. I think you see where the math is coming from here. All right. Then we have to figure in all the ATP that can be made from the citric acid cycle, because the 8-acetyl-CoA you make from the 1-palmitoyl-CoA molecule goes into the citric acid cycle. And then this is just kind of review of the citric acid cycle. And so in this case, we do make some ATP directly, right? And so this is not through cofactors. This was the substrate level phosphorylation reaction that occurs in the citric acid cycle. So I'm just going to call this direct ATP production. So I made a statement a while ago. There's no direct ATP formation in beta oxidation. Well, that's true, because beta oxidation are those 4 reactions that occur to break off acetyl-CoA. But there is ATP production, direct ATP production, once acetyl-CoA is made and flows into the citric acid cycle. So, drum roll please. You go through all of this. For 1 molecule of palmitoyl-CoA, you get 108 ATP. 108 ATP. And let's do the net reaction. Now, I think in the book 17.4, 17.5, and 17.6 kind of review this, but I'm going to do 17.6. Let's just cut to the chase. Let's do the net reaction. So a palmitoyl CoA molecule, again 16 carbons. Again, this is the final net reaction involving all the way to the end here. 23 molecules of oxygen, 108 inorganic phosphate plus 108 ADP yields a molecule of coenzyme A. You got to kick off that CoA plus 108 ATP plus 16 CO2 plus 23 H2O. Wow, that is the net reaction at the very end. And it shows clearly that every carbon in a molecule of palmitoyl-CoA, when metabolized, when broken down, all those carbons end up as carbon dioxide. So I'm going to give you a paper on this in class, supplementary notes, but the question is, where does fat go when you lose weight? Well, I think Noah mentioned this in class. You basically exhale it as carbon dioxide. Alright, so fats are much more energetically dense than carbohydrates. We've talked about this before, and this kind of gives you a clue of why that may be the case. Alright, let's do a few other things here. This video is taking longer than I wanted, but that's life, I guess. So, you know, we just went over beta oxidation of a saturated fat, by the way. Palmitoyl-CoA is saturated. Palmitic acid is a saturated fatty acid. But we also have MUFAs and we also have PUFAs. I'm going to give you a little bit of information on oxidation of a MUFA, but we're not going to talk about beta oxidation of a PUFA. I just don't see the point in that. Let's do one with a MUFA. And here we go. Here is a case where the fatty acyl-CoA is a monounsaturated fatty acid. It's oleoyl-CoA, and the double bond is cis, as you see there. And how is the beta oxidation of this molecule going to be different than palmitoyl-CoA? Well, at first, it's not different. You keep on doing the same thing. Again, you activate it, you transport it, then you have those 4 reactions that release 2 carbon units as acetyl-CoA. For the first 3 cycles, for oleoyl-CoA, it does not matter. It's the same as palmitoyl-CoA. And then ultimately, you will get this intermediate, if you do 3 rounds of this beta oxidation, you get cis delta 3 dodecanoyl CoA. Well, guess what? We don't need that. We need trans delta 2. So when you have a MUFA, everything goes the same as a saturated fatty acid until you get close to this double bond that you encounter, and you get a cis delta 3 intermediate instead of a trans delta 2. Well, guess what? We have an enzyme for that. Delta 3 delta 2 enoyl CoA isomerase. Again, this converts a cis delta 3 to a trans delta 2. This trans delta 2 should look very familiar to you because that's the normal intermediate in the breakdown of a fatty acid. And then once you do this, then beta oxidation proceeds normally. So again, you're still going to release all the carbons. You're still going to release. You're still going to get, acetyl CoA made from oleoyl CoA. You're still going to knock off these 2 carbon units. But there's one extra step in here that has to occur to account for this, the fact that naturally occurring MUFAs have cis double bonds instead of trans, right? Cis is the normal double bond configuration. So you get this cis delta 3 intermediate temporarily. We have an enzyme that converts it to a trans delta 2. Again, very difficult chemistry. If I said, hey, do this reaction in the round bottom flask with any available organic reagents you want, good luck with that. That would be very difficult. But this enzyme can make it happen. Now, here's the question. What if you had 2 fatty acids? First of all, oleoyl CoA is 18 colon 1. So let's go back to what I said a while ago. And you break this down, how many acetyl CoA are you going to get? Well, you're still going to get what? Well, there's 18 carbons, so you're going to get 9 acetyl CoA. So you're going to get those 6 here, 7, 8, 9 from up there. Okay? But what I'm asking you now is, what if you had 18 colon 0 and 18 colon 1? And both of these undergo beta oxidation. Here's the question. Would you get the same number of ATPs produced? Man, that's a great question. So you break down the 18 colon 0, just like we broke down palantoyl CoA, but this one has 2 more carbons, right? But you break it down the same way. Then you break down 18 colon 1 like oleoyl CoA up here, just like you would there. You're still going to get 9 acetyl CoA for both of those. But the question is, in the end, when you do the summary, are you going to get the same number of ATPs produced from the breakdown of these 2 fatty acids? I'm going to leave that for you to ponder and think about, because this is a really good question. All right, let's keep going. Page 16, I'll be honest with you, I don't want to spend a lot of time on because we're kind of getting behind. I do want to make a big point is some marine organisms and plants have fatty acids with an odd number of carbons. Remember, in animals, that's not an issue, but for some marine organisms and plants, we do have 3 carbon. We do have odd number fatty acids. And think about that. If you have a fatty acid with an odd number of carbons, in the end, instead of making 2-acetyl-CoA, when you metabolize these fatty acids, instead of making 2-acetyl-CoA at the end, you're going to make an acetyl-CoA and a propionyl-CoA. This is a 3-carbon CoA. The whole point of this page is that we have to have a way to metabolize propionyl-CoA. Okay? And through this complicated series of events that I'm not really going to ask you about, we can convert propionyl-CoA, to succinyl-CoA, and of course succinyl-CoA can just basically move into the citric acid cycle. So, we have a way to take all this propionyl-CoA that we might make from ingesting plants or marine organisms through the breakdown of those fatty acids to propionyl-CoA. We have a way to convert that to a citric acid cycle intermediate. I'm not going to really talk about this. It pains me, but that's the way it goes. So let's end this with the regulation of fatty acids. So how do we regulate fatty acid oxidation? Well, this is a very important area. So in the liver, fatty acyl-CoAs formed in the cytosol has two major pathways. Okay? Number one, you can break it down by beta oxidation by enzymes in the mitochondrion. We talked about that before. We'd have to transport the fatty acyl-CoA into the mitochondrion and undergo beta oxidation. The other possibility is to take fatty acyl-CoA and to make triglycerides with it. We haven't talked about that. We will a little bit later on, but this is called fat synthesis. How do you make from fatty acids or activated fatty acids triglycerides? Because triglycerides are the main storage form. And we also make phospholipids, like membrane lipids, from fatty acids as well, right? So all of this occurs in the cytosol. So these enzymes are in the cytosol, and beta oxidation is in the matrix of the mitochondrion. So that's where the enzymes of beta oxidation are at. So how do we regulate these two things? So what's going to drive us toward the breakdown of fatty acids through beta oxidation, or the synthesis of triglycerides from fatty acids? Well, I don't think it's going to shock you when I tell you there's going to be a significant hormonal influence. All right. Let's go here to page 18. Here we go again. Indeed. So this is a big page. This is big time. Here we go. Let me tell you the story here. This is beta oxidation. We just did this, okay, in this video and in class. We have fatty acyl-CoA. There's a carnitine acyltransferase 1 that converts it to the fatty acylcarnitine. Again, this is review. We've talked about this. Once we get the fatty acylcarnitine in the mitochondrial matrix, it goes back to fatty acyl-CoA, and then here are our 4 reactions in beta oxidation. Wow, we went into detail about that. What we know is that there's a molecule called malonyl-CoA. And malonyl-CoA, right here, can, look at this, ... Boom, that's an X, ladies and gentlemen. Malonyl-CoA blocks carnitine acyltransferase 1. If you block carnitine acyltransferase 1, you basically short-circuit, disrupt beta oxidation. And guess how we make malonyl-CoA? We make it from acetyl-CoA and fatty acid synthesis. So we're not going to go into great detail about it, but we are going to go into a little bit of detail to understand this dual regulation. So the major player in this regulatory scheme on page 18 is an enzyme called ACC. And that's not the Atlantic Coast Conference for you basketball fans. This is acetyl-CoA carboxylase. Okay, what does acetyl-CoA carboxylase do? It converts acetyl-CoA to malonyl-CoA. Here it is right here. Here's ACC. Like so many other enzymes you're familiar with, ACC is under control by phosphorylation. It can be phosphorylated by our old friend protein kinase A. And there's another kinase called AMPK that can do this. Let's not worry about AMPK now. ACC is a target protein for protein kinase A. And when ACC is phosphorylated, it's turned off. So protein kinase A turns off ACC. And if you turn off ACC, you don't make malonyl-CoA. Okay, that's where we're going with this. Guess how you can get ACC back in the game? Activate it. You can dephosphorylate it. I wonder what would dephosphorylate ACC. I don't know. Perhaps a phosphatase called PP1. And I wonder what hormone that we've mentioned, a million and one times, activates PP1. Insulin. So here we go, ladies and gentlemen. Let's think about this. Let's take let's do some detail trains. And the way this image is set up, we're going to really talk about in terms of consumption of dietary carbohydrates. Okay, so let's go here, and well, it's either the consumption of them or lack of them. So let's start with high blood glucose. Okay, so carbohydrate rich meal, you get high blood glucose. I'm gonna pause this just for a second. I will be back. All right, and we're back. So high blood glucose, carbohydrate rich meal, insulin secretion. We're right here, ladies and gentlemen. We're right down here. Insulin secretion. Insulin activates PP1. We know that. We dephosphorylate ACC. ACC is active, and acetyl-CoA makes malonyl-CoA. Malonyl-CoA will make fatty acids in a later chapter, and then fatty acids can be used to make triglycerides or tag molecules. We've already talked about insulin drives fat synthesis. This is how it happens. This is a major player in that. High blood glucose, insulin secretion, PP1 activation, dephosphorylation of ACC, activate ACC, acetyl-CoA is converted to malonyl-CoA, malonyl-CoA is converted to fatty acids are converted to tags. Also, malonyl-CoA blocks fatty acid beta oxidation. That's what this is telling you here. Malonyl-CoA blocks carnitine acyltransferase 1. It's an allosteric inhibition. And so not only is fatty acid synthesis promoted via insulin action, beta oxidation is suppressed. Also, when we talk about this glucose making acetyl-CoA, you know from Biochem 1 that insulin also activates many steps in glycolysis as well. So insulin drives the formation of acetyl-CoA, and you now know it drives the formation of malonyl-CoA from acetyl-CoA. Malonyl-CoA goes to make fatty acids, then tags. Malonyl-CoA shuts down, suppresses beta oxidation. By the way, before I forget, remember table 15-5? ACC transcription. Well, let's do it this way. insulin activates transcription, increases the, just say it this way, insulin increases the expression of ACC. And we talked about table 15-5. So insulin does all this work through PP1. It also increases the expression of the enzyme ACC. And so all this works together to drive fat formation. Now, on the other hand, low blood glucose. Do you want to be making fats during times of low blood glucose? Oh, I don't think so. You better be breaking down fats in beta oxidation to make ATP to drive gluconeogenesis. So, how's that going to work? Low blood glucose? Here we go. Old friend. Glucagon secretion by a complicated series of events that you know like the back of your hand. Glucagon activates protein kinase A. Protein kinase A phosphorylates ACC. And when ACC is phosphorylated, let me put the arrow back into here. When ACC is phosphorylated, it's inactive. If ACC is inactive, you don't make malonyl-CoA. And if you don't make malonyl-CoA, malonyl-CoA cannot inhibit carnitine acetyltransferase 1. Therefore, low blood glucose, glucagon, protein kinase A, inactivation of ACC, we don't make fats because we don't make malonyl-CoA, but we activate beta oxidation, or we can run beta oxidation because malonyl-CoA is not being made that can suppress it. So, ultimately, here we go again, just like the page says. You need to be able to look at this and how does hormones work in the breakdown and the synthesis of fats. We've already talked about this in this class. Hormone sensitive lipase, gotta know that. Now ACC, and then add those two enzymes to all the other ones we've talked about in Biochem 1, and a much bigger picture of how insulin does its job and how glucagon does its job is emerging. And then we're going to keep building on this a little bit more as we go forward. All right, ACC, very important. Let's do just one more page here. There's a couple other control points in beta oxidation. Again, the enzymes we're talking about here are on page 12 of the notes. Here's the dehydrogenase, the beta hydroxy acyl-CoA dehydrogenase. This enzyme is controlled by NAD ratio, the concentration, the ratio of those two concentrations. So basically, if the concentration of NADH is high, ladies and gentlemen, we talked about this in Biochem 1 with the citric acid cycle. So I'm getting the feeling of an analogy coming on here, okay? But right now, a high NADH concentration will lead to a lower enzyme activity for this dehydrogenase. That makes sense because you're making NADH. So a high NADH concentration will tend to suppress this enzyme. Again, the analogy here is our old friend isocitrate dehydrogenase in the citric acid cycle, which was controlled by NADH, NAD plus concentration ratio. Again, this is controlling beta oxidation. The other example is the thiolase that we've talked about. It is inhibited by acetyl-CoA. Well, this is kind of textbook product inhibition. If the concentration of acetyl-CoA is high, basically you suppress the thiolase activity. There's an analogy here. The analogy here is pyruvate dehydrogenase. That catalyzes the bridge reaction, where it also was allosterically inhibited by its own product, acetyl-CoA. Same thing here. Same thing here. If acetyl-CoA is plentiful, do we really need to be breaking down fatty acids in beta oxidation to make more acetyl-CoA? I think not. Back to the first example on this page. If the concentration of NADH is high, do we really need to be running beta oxidation that ultimately is going to make a lot of NADH? Probably not. So again, these are two important control points in beta oxidation, and then add that in to the hormonal regulation on the previous page. All right, this went longer than I wanted. I'm sorry, but we will stop here for this video, and then we're going to, in class on Friday, continue on with this chapter and talk about ketone bodies. All right, thank you.